Hello friends, good afternoon and welcome to the EduSat network. Our topic of discussion is part of our series on chemical reactivity and mechanisms, and friends, the specific topic for today shall be alcohols and its chemical reactions, and as part of this topic, preparations have already been discussed, and now the chemical reactivity of chemicals of this particular segment shall be discussed by our subject expert, whom I would like to introduce now. We have this in our studio, Dr. Vandana, Assistant Professor, Department of Chemistry, Dayal Singh College, University of Delhi, and ma'am has been guiding us throughout this series, being associated with us closely, and with this I welcome her to the studio. Ma'am, thank you so much for coming.
Thanks for nice introduction. Hello viewers, in the series of chemical reactivity and mechanism, I have already discussed about the introduction and preparations of alcohols. In today's lecture, I have took for you the reactions of alcohols or alkanols. The highlights for the today's lectures are reactions involving cleavage of hydrogen-oxygen bond, reactions with metals, reactions with sodium hydride, reaction with sodium amide, reaction with alkyl lithium and Grignard reagents. The other points are reaction with alkyl halides, reaction with carboxylic acids, reaction with acid chlorides, reaction with acid anhydrides, reaction with sulfonyl chlorides, reactions involving cleavage of carbon-oxygen bond, and reactions with hydrogen halides, reaction with thionyl chloride, reaction with ammonia, and formation of esters of organic esters. So, we have started the reactions of alcohols. Polarization of OH bond, this OH bond makes the hydrogen partially positive charge. This is the reason alcohols are weak acids, and polarization of this carbon oxygen bond makes the carbon partially positive charge susceptible to nucleophilic attack, as hydroxyl ion being strong base, poor leaving groups. So, you can see because of this electronegativity difference, this carbon will behave as partially positive charge, as well as hydrogen will behave as partially positive charge, and oxygen will behave as partially negative charge. The electron pair on oxygen atom make it both basic and nucleophilic. In presence of strong acid, alcohols acts as base and accept proton. You can see this is the alcohol COH, this is a strong acid HA. This oxygen atom, as it contains the lone pair of electron, will accept this proton from the strong acid to form the protonated alcohol. Now, this protonated alcohol can easily attacked by this nucleophile and will give you the substitution reaction. Hence, protonation of alcohol converts a poor leaving group, that is hydroxyl group, into the good leaving group. This is your protonated water molecule, and this substitution preferably takes place by the SN2 mechanism, substitution nucleophilic bimolecular, means the removal of this protonated water molecule as well as the attack of this nucleophile to this partially positive charged carbon will takes place simultaneously. That does it mean SN2 mechanism. Now, carbon become more susceptible to nucleophilic attack, as with respect to SN2, SN1 also takes place to give the product. So, you can see here how alcohol will undergo SN2 reaction to give the protonated ether. This is ROR. This discussion concludes that reactions of alcohols involves cleavage of oxygen-hydrogen bond may be classified into two categories. First, the reactions in which alcohol act as acids and form alkoxide salts. Next, reactions in which alcohols and alkoxide ions act as nucleophiles and bring about nucleophilic substitution of different electrophilic substrate. first reaction I have discussed, I am discussing here is alcohol as acids. Alcohols are weak acids, except methanol there are weaker acids than water molecule, or we can say except methanol all the alcohols are stronger acid than water molecule. Lesser acidity of sterically hindered alcohols such as tertiary butyl alcohol shows due to the solvation effect. With unhindered alcohol, water molecules are able to surround and solvate the negative oxygen of the alkoxide ion. This is your alkoxide ion. When alcohol loses a proton to a strong base. If R group is bulky, solvation of alkoxide is hindered and alkoxide is not so effectively stabilized, consequently alcohol is weaker acid. You can see this is alcohol, this is water molecule and it will gives you alkoxide ion. If it is unhindered, it will be solvate and thus loses a strong base. If this R group is bulky and this alkoxide is hindered, the alkoxide is not so effectively stabilized by the, thus relative stability of alkoxide ions in solution is greater the R group, greater will be the, lesser will be the relative stability of alkoxide ion. The relative acidity of alcohol is tertiary will be less than secondary and secondary will be less than primary and primary will be less than methanol, that is CH3OH. Phenols are considerably more acidic than alcohols because phenoxides ion, or we can say the conjugate bases of phenols are stabilized by resonance, whereas alkoxide ions, the conjugate bases of alcohols do not have resonance structure and are less stable. The relative acidity of alcohols in gas phase is just reverse. Now, tertiary will be more stable than secondary, then primary and then methanol. In this case, the relative stability of alkoxide ion depends on the polarization effect and not on the solvation effect. And this effect found in the solution where solvation is the stabilizing factor. Next reaction is the reaction with metals. Alcohols react with strongly electropositive metals, for example, sodium, potassium, magnesium, aluminium to form the corresponding metal alkoxide with the liberation of hydrogen gas. You can see here the reactions of ethanol with sodium will give you sodium ethoxide, then trimethyl alcohol when reacts with potassium will give you potassium alkoxide, then methanol when reacts with magnesium will give you magnesium alkoxide, and isopropyl alcohol when reacts with aluminium will give you aluminium isopropoxide with the liberation of hydrogen gas in all reactions. Alkoxide ions are stronger bases than the hydroxide ion. So, what will happen? Metal alkoxide readily react with water to regenerate the corresponding alcohols and sodium hydroxide. This is the reaction, how it follows. Sodium ethoxide when react with water molecule to give the alcohol ethanol. Next reaction is reaction with sodium hydride. Hydride ion, that is H minus, is a stronger base than the alkoxide ion. Alkoxide is what? RO minus. So, alcohols donate a proton to the hydride ion to form the hydrogen gas and are themselves converted to alkoxide ion. Here is the example. When methanol reacts with sodium hydride, it will give you sodium methoxide along with hydrogen gas. Next reaction is with sodium amide. The amide ion, that is NH2 minus, is a stronger base than alkoxide ion. So, they abstract a hydrogen from alcohol to form alkoxide ions and ammonia. Here is the reaction. When sodamide reacts with ethanol, it will give you the sodium ethoxide. Sodium hydroxide practically does not react with alcohols to form alkoxide salts because hydroxyl ion is a weaker base than alkoxide ion. Next reaction is with reaction with alkyl lithium, that is RLi, and Grignard reagent, that is RMGX. As we are very much aware of the fact that the carbon metal bond in alkyl lithium and alkyl magnesium halide are highly polarized. So, these compounds behave as electropositive as they have contain alkylide ion, that is R minus. Alcohols are much stronger acids than alkanes, and consequently alkanides ion are the stronger bases than alkoxide ions. So, alcohols react with alkyl lithium and alkyl magnesium halides to form the corresponding alkoxide and alkanes. Here is the example. You can see when tertiary butyl lithium reacts with methanol, it will give you 2-methyl propane along with lithium methoxide. Another reaction is, you can see here there are two reactions. Now, alkenide ions, that is RC triple bond C negative, are also stronger bases than the alkoxide ion. So, they react with alcohols to form corresponding alkoxide and alkenyls. Here is the example. When this sodium alkenide react with ethanol, it will give you acetylene along with sodium ethoxide. We can thus place alcohols in the sequence of acidity related to other compound as follows. Relative acidities are: water molecule will be greater acidic than alcohol, it will be greater than acetylene, it will be greater than ammonia, and it will be have greater acidity than alkane. Relative basicities are as follows. You can see the order. Hydroxide ion will be the lesser basic as compared to the alkoxide ion, that is RO minus. It will be less basic than alkylide ion, it will be less basic than amide NH2 minus ion, and then alkanide ion, that is R negative. Next reaction of alcohol is alcohol behaves as nucleophiles. So, we will discuss about the nucleophilic substitution reactions of alcohols. First is the reaction with alkyl halides and with sulfonates. Sodium and potassium alkoxides reacts with primary alkyl halides and tosylates by SN2 mechanism to yield the ethers. The substrate must bear a good leaving group. This reaction is known as Williamson ether synthesis. Here are the examples. When sodium ethoxide reacts with ethyl bromide, it will give you diethyl ether. You can see diethyl ether, ROR. Next, with potassium, trimethyl potassium, it will reacts with ethyl bromide to give the ether, again a ether is formed. Next reaction is with sodium cyclopentoxide. When reacts with methyl iodide, it will give you cyclopentyl methyl ether. Next reaction is with sodium methoxide. When reacts with tosylate sulfonate, that is ethyl paratoluene sulfonate, it will give you ethyl methyl ether along with sodium paratoluene sulfonate. Here alcohols are weak nucleophiles. Best results can be obtained when reacts with primary alkyl halides with sulfonates or sulfates. However, when tertiary alkyl halides are treated with large excess of alcohols, the mechanism is SN1 rather than SN2. Substitution also favored over elimination at lower temperature. Secondary alkyl halides and tosylates reacts with alkoxide to yield both ethers and alkenes. You can see when sodium methoxide reacts with cyclohexyl paratoluene sulfonate in DMSO, dimethyl sulfoxide solvent, it will give you cyclohexene in 85% along with cyclohexyl methyl ether 15%. So, here alkene predominates. Tertiary alkyl halides and sulfonates reacts with metal alkoxide to give alkenes almost exclusively mainly by elimination by molecular reaction. Here is the example: when sodium methoxide reacts with tertiary butyl bromide, it will give you isobutylene. Next reaction is with reaction with carboxylic acid. When a carboxylic acid is heated with excess of an alcohol in the presence of a small amount of concentrated sulfuric acid or dry hydrogen chloride gas, an ester is formed. This is Fischer esterification reaction. It is a reversible reaction. So, alcohol is taken in large excess in order to get a good yield of ester. The substitution occurs by the way of addition elimination mechanism. These are the examples: when acetic acid reacts with ethyl alcohol in large amount, because it is a reversible reaction, in order to get the product in good amount we have to take the ethyl alcohol in large amount. So, here we get the ethyl acetate, an ester. Next reaction is benzoic acid. When reacts with methyl alcohol in large amount with H2SO4 and heat, we will get the methyl benzoate. This is the mechanism. How mechanism is follows. You can see this is carboxylic acid, RCOOH, and we are very much aware of the fact that carboxylic acid and its derivatives gives substitution reaction preferably. This is the alcohol, protonated alcohol. It attack to the carboxylic acid, then this proton will be acquired by this oxygen molecule, hence we get the protonated carboxylic acid. Now, this alcohol molecule will attack to this carbon because this electron will attracted by this oxygen. So, we get the tetrahedral intermediate addition product. This proton you can see is abstracted by this alcohol molecule, we get the tetrahedral intermediate. Again it is attacked by the protonated alcohol molecule. So, we get the tetrahedral intermediate in which this hydroxyl group is converted to the protonated water molecule, and we are very much aware of the fact that in comparison to hydroxyl group, this water molecule is a good living group. So, there is a elimination of water molecule and then we get the protonated carboxylic acid, and this proton will be abstracted by the alcohol to give the ester. So, this is the mechanism how carboxylic acid will convert it to ester with the help of alcohol. The following experiment was carried out to prove the acyl oxygen bond cleavage occurs during the esterification. Benzoic acid was esterified with labeling oxygen molecule as 18. The product methyl benzoate was found to be oxygen labeled, but the water produced is unlabeled. So, you can see this is the benzoic acid, this is methanol. Here we have labeled this oxygen 18 and it shows the cleavage of this carbon oxygen bond, and you will get the ester in which this oxygen will comes from the methanol. Reactivity of alcohols and acid towards esterification. The rate of esterification is very sensitive to steric hindrance. The presence of bulky group near the site of reaction, whether in the alcohol or in the acid, slows down the esterification. Thus, increasing number of alkyl substituent at the alpha carbon of either carboxylic acid or alcohol decreases the rate of reaction, that is esterification. So, this is the order of reactivity for acids. Formic acid will be has greater reactivity than acetic acid, and you can see as the number of substitution increases, the reactivity decreases. Order of reactivity of alcohols. Primary alcohol, that is methanol, will have greater reactivity in comparison to 2 degree, that is ethanol. It has greater reactivity than 3 degree, that is tertiary butyl alcohol. Tertiary butyl alcohol undergoes esterification very slowly. It mainly undergoes dehydration to form isobutylene. 2,4,6-trimethyl benzoic acid cannot be esterified by the usual processor because the carboxylic group is too crowded by the 2-methyl substituent at ortho position to form a tetrahedral intermediate by the addition of alcohol. Next reaction is reaction with acid chloride. Alcohols reacts with acid chloride in the presence of tertiary amine base such as pyridine or triethylamine to form esters. The base removes hydrogen chloride formed in the reaction as its chloride salt. This is the example. When acid chloride react with alcohol in presence of pyridine, it will give you ester RCOOR along with HCl. These are the examples. When acetic chloride react with ethyl alcohol in presence of pyridine will give you ethyl acetate along with the salt pyridinium chloride. Another reaction is with benzoyl chloride. When react with tertiary butyl alcohol, it will give you tertiary butyl benzoate in presence of pyridine along with the salt of pyridine. Next reaction is with benzoyl chloride. When reacts with cyclohexanol in presence of pyridine, it will give you cyclohexyl benzoate along with the salt of pyridine, that is pyridinium chloride. Mechanism: the acid chloride undergoes a nucleophilic substitution of chlorine at the acyl carbon by alcohols through addition elimination mechanism as shown below. You can see this is acid chloride RCOCl. Because of this electromeric effect, because of this alcohol ROH, this pi bond will shift it towards the oxygen atom being an electronegative atom, and it becomes the electropositive partially. So, this oxygen will attack to this carbon, will give you this addition product at tetrahedral intermediate. When this form, there is a liberation of chloride ion because of this arrangement, rearrangement. So, we will get here the protonated, we will get here the addition product. Now, this proton will abstracted by this base, that is pyridine, to give the ester along with the salt of pyridine, that is pyridinium hydrogen, hydrogen. Reaction with acid anhydrides. Alcohols react with acid anhydride to form esters. The reaction is usually carried out in the presence of pyridine, which neutralizes the carboxylic acid formed in the reaction as a co-product. Here is the representation. Acid anhydride when reacts with alcohol to give the ester along with the carboxylic acid. These are the examples. This is acetic anhydride when reacts with ethyl alcohol in presence of pyridine to give the ethyl acetate as well as the pyridinium acetate. Another example is cyclopentanol when reacts with this diketone pyridine in presence of pyridine to give the cyclopentyl acetate along with the salt. The reaction involves nucleophilic substitution at one of the two carbonyl group of anhydride by addition elimination mechanism. You can see this carbon will attack by this alcohol to give the addition product, that is tetrahedral intermediate. Because of this rearrangement, you will get this addition product. So, there is a elimination of this group, and this proton will be abstracted by this pyridine to give this product, and we will get the ester. So, here we get the pyridinium ion. Next reaction is with reaction with sulfonyl chlorides. Alcohols react with para-toluene sulfonyl chlorides in presence of pyridine to form alkyl para-toluene sulfonates. Similar reaction occurs with benzene sulfonyl chloride and methane sulfonyl chloride. These reaction involves the cleavage of oxygen hydrogen bond and not carbon oxygen bond. If the alcohol had chiral, then no change of configuration occurred, that the stereochemistry will be the same. If the starting material is R, the product will be R. If starting material has S configuration, the product will have the same configuration, that is S. It means there will be no change in the configuration. Alkyl sulfonates, being good leaving group, may undergo nucleophilic substitution reaction. If nucleophilic substitution is SN2, then we know inversion of configuration will takes place. Here are the examples. Ethyl alcohol, when reacts with this para-toluene sulfonyl chloride in presence of pyridine, will give you ethyl para-toluene sulfonate along with the pyridinium salt. Another example is cyclohexanol, when reacts with para-toluene sulfonyl chloride in presence of pyridine, will give you this addition product, that is cyclohexyl para-toluene sulfonates. Para-toluene sulfonyl chloride is commonly called tosyl chloride and denoted as TSCl. For short notation, we call this para-toluene sulfonates as tosylates. The tosylate group is OTS, is an excellent leaving group and can be displaced by a variety of nucleophiles. So, conversion of an alcohol to a tosylate followed by nucleophilic displacement provides an excellent synthetic way to a variety of products. Here are the examples. When 1 degree alcohol reacts with this tosylate, will give you ether in presence of sodium ethoxide, and when this reacts with tosylate in presence of potassium cyanide, will give you alkyl cyanide. In presence of sodium acetate, it will give you alkyl acetate, and in presence of sodium iodide and acetone, it will give you alkyl iodide, that is alkyl halide. Mechanism: the reaction is a nucleophilic substitution of chlorine attached to the sulfonate group by alcohol and proceeds by addition elimination mechanism. You can see how this alcohol attached to this sulfur atom, because of this electromeric effect there is a difference in electronegativity. So, it will attack to this sulfur atom and we will get this addition product tetrahedral intermediate, and this proton from this tetrahedral intermediate will be abstract by the pyridine to give this alkyl para-toluene sulfonate. Next type of reactions are the reactions involving cleavage of carbon oxygen bond. For these kind of reaction we are taking first the reaction with the hydrogen halides. Alcohols reacts with hydrogen halides to form alkyl halides. This is a nucleophilic substitution reaction. This is the representation of reaction. Alcohol when reacts with hydrogen halide will give you alkyl halide. The order of reactivity is 3 degree will be have greater reactivity than 2 degree and 2 degree have greater reactivity than 1 degree alcohol. Order of reactivity for hydrogen halides are hydrogen iodide will be more reactive than hydrogen bromide and hydrogen bromide will be more reactive than hydrogen chloride. Hydrogen fluoride is unreactive. The order of reactivity of hydrogen halide is in accordance with the nucleophilicity of the halides ions. This is the mechanism with tertiary butyl alcohol and hydrogen hydrochloric acid. In dehydration reaction, the carbon cations loses a proton in an E1 reaction to form an alkene. In the formation of alkyl halide, the carbocation reacts with nucleophile in an SN1 mechanism. So, you can see here mechanism with tertiary butyl alcohol. First of all, it will give you the protonated alcohol and then there is a formation of carbocation, tertiary carbocation. This tertiary carbocation will attacked by the nucleophile chloride will give you tertiary butyl halide, that is chloride. Primary alcohols undergo SN2 type mechanism. The halide ion displaces the water molecule to produce a alkyl halide. Although bromide and iodide ions are strong nucleophile, substitution does not take place as leaving group hydroxyl ion is strongly basic. So, you can see the reaction of with bromide ion, that is leaving group here is hydroxyl ion and attacking group here is bromide ion. So, the reaction will not take place because bromide ion are strong nucleophile than this hydroxyl. Order of nucleophilicity of halide ions. This is the order of nucleophilicity. Iodide will have greater nucleophilicity than bromide ion, it has greater than chloride ion and it has greater than fluoride ion. The primary alcohols reacts with hydrogen halides by SN2 mechanism, whereas secondary and tertiary alcohols reacts with SN1 mechanism because of the stability of carbocation. Next reaction is with reaction with hydrogen chloride. The reactions of primary and secondary alcohols with hydrogen chloride are relatively slow because these alcohols are less reactive and the chloride ion is relatively weaker nucleophile. These reactions are usually carried out in the presence of anhydrous zinc chloride, a Lewis base acid which catalyzes the reaction by increasing the leaving ability of hydroxyl group through its coordination with oxygen atom. You can see here this is alcohol and this is zinc chloride, it gives the addition product. This addition product will increase the leaving ability of this group. So, this group OH ZnCl2 is a better leaving group than the hydroxyl group. The tertiary alcohols and benzylic and allylic alcohols reacts with HCl smoothly and do not require any catalyst. So, here you can see how the reaction proceed with the addition of better leaving group, that is this ZnOHCl2 minus. Hence, the chloride ion now easily attack to this group. These are the examples when ethyl alcohol reacts with HCl in presence of ZnCl2 to give the ethyl chloride, isopropyl reacts with HCl to give the isopropyl chloride, and tertiary butyl alcohol will give you tertiary butyl chloride. So, you can see as the degree of alcohol is increases, we do not need the catalyst of zinc chloride. Reaction with hydrogen bromide. The reaction of primary alcohol with hydrogen bromide is generally carried out in the presence of small amount of concentrated H2SO4 as catalyst. Secondary and tertiary alcohols react with hydrogen bromide smoothly without any catalyst. These are the reactions examples. N-propyl alcohol will give you N-propyl bromide in presence of sulfuric acid when reacts with hydrogen bromide. Another example is butane 2-ol when reacts with hydrogen bromide in presence of heat will give you 2-bromobutane, and 2-methyl butane 2-ol when reacts with the hydrogen bromide will give you 2-bromo-2-methyl butane. Next reaction is with reaction with hydrogen iodide. All three classes of alcohols, that is 1 degree, 2 degree, 3 degree primary, secondary or tertiary alcohols reacts with hydrogen iodide smoothly and do not require any catalyst because the iodide ion is the strongest nucleophile among the halides ion and hydrogen iodide is the strongest acid among the hydrogen halides. So, here are some examples when alcohol reacts with hydrogen iodide to give the alkyl halide. This is the primary alcohol and this is the tertiary alcohol. Next is the rearrangement type of alcohols. Reactions of alcohols including rearrangement. The reactions of secondary alcohols with hydrogen halides are sometimes accompanied with rearrangement. The rearrangement occurs only when the initially formed carbocation can itself change to a more stable carbocation either by 1,2 hydride shift or by 1,2 alkyl shift or by ring expansion. Most primary alcohols do not undergo rearrangement. For example, the reaction of 3-methylbutane-2-ol with hydrogen bromide yields 2-bromo-2-methylbutane as the major product and 2-bromo-3-methylbutane as the minor product by the rearrangement of the carbocation. Here is the representation of reaction. You can see when this alcohol is attacked by the hydrogen bromide, first of all it will give this addition product, then there is a elimination of good leaving group, that is OH2, and formation of 2-degree carbocation. You can see this is 2-degree carbocation. Now this 2-degree carbocation will convert it to 3-degree carbocation by rearrangement by 1,2 hydride shift to give the more stable carbocation. Hence, we will get the product 2-bromo-2-methylbutane by the elimination of this bromide ion, that is this hydroxyl group will substitute by this bromide ion with the minor product 2-bromo-3-methylbutane by the 2-degree carbocation intermediate. So, you can see there is a rearrangement of more stable carbocation from 2-degree to 3-degree carbocatons. Next reaction is with the reaction with thionyl chloride. Alcohols reacts with thionyl chloride to form alkyl chlorides. You can see this is the alcohol, this is the thionyl chloride, it will give you the alkyl chloride. This is the example when butane 1-ol reacts with thionyl chloride, it will give you 1-chlorobutane. This reaction is very interesting regarding its stereochemical aspect. When the reaction is carried out in presence of pyridine, it undergoes SN2 reaction with the inversion of configuration as the substrate center. On the other hand, when the reaction is carried out in ether solvent in the absence of pyridine or any other base, it undergoes SNI reaction, that is retention of configuration at the substrate center. Substitution nucleophilic intermolecular. Alkyl chlorides are generally prepared by this method because this reaction is rapid and relatively free of side reactions as we got in the previous reaction. Moreover, the purification of product, that is alkyl halide, which is the byproduct, the product is easily because the co-products SO2 and HCl escapes as gases. These are the examples when octane 2-ol reacts with thionyl chloride, undergoes SNI mechanism to give the 2-chlorooctane, that is there is a substitution by nucleophile, but internally the mechanism undergoes internally and the product will get the retention of configuration, that is this reactant is R, the product will produces R. Next reaction is octane 2-ol when reacts with thionyl chloride in presence of pyridine. This reaction is SN2. We have already stated if pyridine is there, the mechanism will be SN2 because it is a strong base. So, now we get the product S as compared to the substrate R. Here the inversion of configuration and the product is 2-chlorobutane mechanism. It involves initial formation of alkyl chlorosulfide. You can see alkyl, this is the alcohol, primary alcohol attacked by this thionyl chloride. It is the alkyl chlorosulfide. Then the chloride ion bring about SN2 displacement of a very good leaving group, and you can see there is a attacking of chloride ion to this R group and you will get the alkyl chloride. Now reaction with ammonia. When a mixture of alcohol, ammonia is passed over alumina heated at 360 degrees Celsius, a mixture of primary, secondary and tertiary amine is formed. You can see the reaction. This is ethyl alcohol. First of all will give you the ethyl amine primary, then it will give you diethyl amine and then it will give you triethyl amine when reacts with ammonia in presence of alumina Al2O3 and at the temperature of 360 degrees Celsius. Next reaction is the formation of esters of inorganic acids. Alcohols reacts with strong inorganic oxo acids to form the corresponding esters. Sulfate esters. Ethyl alcohol reacts with concentrated sulfuric acid to form ethyl hydrogen sulfate. You can see the reaction. This is the ethyl alcohol. When reacts with sulfuric acid, this proton will be taken up by this alcohol and will give you the ethyl hydrogen sulfate by SN2 mechanism. That is, there is a substitution reaction. When ethyl hydrogen sulfate is heated with excess of ethyl alcohol at 100 degrees Celsius, diethyl sulfate is formed. So, here is the representation of reaction. You can see that this is the ethyl alcohol. When reacts with this ethyl hydrogen sulfate, first of all it will give you this, this proton will be abstract by this alcohol to give the better leaving group, that is OH2. When this leaves, there is a substitution reaction at this carbon by SN2 mechanism by this group to give the diethyl sulfate. This is the ethyl sulfate ions as nucleophile attack to this carbon and there is a elimination of good leaving group, that is water molecule, because of this positive charge on this electronegative oxygen atom. On the other hand, when ethyl hydrogen sulfate is heated with excess of ethyl alcohol at 140 degrees Celsius, diethyl ether is formed. So, you can see this is the ethyl alcohol. When reacts with ethyl hydrogen sulfate, it undergoes SN2 mechanism and the reaction takes place at 140 degrees Celsius. First of all, there is a protonation at oxygen atom and then there is a formation of diethyl ether along with sulfuric acid. This proton will be abstract by this anion, that is hydrogen sulfate anion. Sulfate esters can also be prepared by the reactions of alcohols with sulfuryl chloride. For example, methyl alcohol when reacts with sulfuryl chloride, it will give you dimethyl sulfate. Dimethyl sulfate. Sodium salt of long straight chain alkyl hydrogen sulfates are biodegradable synthetic detergents. They are prepared from the corresponding alcohols as follows. You can see the example. This is the lauryl alcohol in presence of H2SO4. First of all, it will give you lauryl hydrogen sulfate, and when it reacts with sodium hydroxide, it will give the salt of lauryl hydrogen sulfate, that is sodium lauryl sulfate. Nitrate esters. Nitrate esters can be prepared by the reactions of alcohol with nitric acid. Care should be taken to avoid oxidation of alcohols by nitric acid. This is the example. When methyl alcohol react with nitric acid, will give you methyl nitrate. These are the another examples. This is glycerol when reacts with nitric acid to give the glyceryl trinitrate. This is the nitroglycerine. And when pentaerythritol reacts with nitric acid, it will give you pentaerythritol tetranitrate, that is PETN. Glyceryl trinitrate, that is nitroglycerine, and pentaerythritol tetranitrate are powerful explosives and the former is also used as vasodilator in the treatment of certain types of heart disease. Next reaction is the formation of phosphate esters by the reaction of alcohol with phosphorus oxychloride. This is the example. Methyl alcohol when reacts with phosphorus oxychloride, it will give you trimethyl phosphate. So, the points we have discussed today are: number 1, the reactions of alcohols, in which first point was reactions involving cleavage of hydrogen oxygen bond, reactions with metals, reactions with sodium hydride, reactions with sodium amide, reactions with alkyl lithium and Grignard reagent, reactions with alkyl halides, reactions with carboxylic acids, reactions with acid chlorides, reactions with acid anhydrides, and reaction with sulfonyl chlorides. Next is the reactions involving carbon oxygen bond. Other reactions are reactions which we have discussed in today's lectures are reactions with hydrogen halides, reactions with thionyl chloride, reactions with ammonia, formation of esters of inorganic salts. So, in the today's lecture we have discussed about the reactions of alcohols or alkanols. For summarize the lecture, I want to put again the reason why alcohols gives two types of reaction, that is alcohols behaves as weak acids and alcohol gives nucleophilic substitution reactions, because the polarization of OH bond makes the hydrogen electropositive as compared to the oxygen, as well as electropositive to the carbon. So, we got two electropositive atoms because of the electronegative oxygen atom. So, polarization of OH bond makes the hydrogen partially positive, and that is why alcohols are weak acids, whereas the polarization of carbon oxygen bond makes the carbon atom partially positive, susceptible to nucleophilic attack, as the hydroxyl being strong base poor leaving group. So, we can see this discussion concludes that reactions in which alcohol act as acids and form alkoxide salts, and reactions in which alcohols and alkoxide ions act as nucleophiles and bring about nucleophilic substitution of different electrophilic substrate. So far we have discussed all the reactions of alcohols. In the next lecture, I would like to take the rest of the reactions of alcohols, that is reactions with phosphorus trichloride, reactions with pentachlorides, and the physical properties of alcohols. If you have any kind of query regarding these lectures in the chemical reactivity and mechanism, you can ask. My email ID is this ronakvandana@gmail.com. So, thank you so much.